All right, good evening to you all. All right, so this actually continuation on our capacitor. All right, so let me show you something quite quickly. Now we have stated that capacitor, all right, in the previous video is a device we use in storing electrical charges. Okay, so now let's look at something here. When you talk about energy stored in a capacitor, all right, energy stored in a capacitor. When you talk about energy stored in a capacitor, all right, what are we talking about? Energy stored in a capacitor. So there are quite a number of things I want to do in this video, and energy stored in a capacitor is one of them. Aside from that, I still want to talk about how to calculate for the half-life, all right, and the charging and discharging of a capacitor, and using the conservation of momentum to determine what happens for your before and after connection in the capacitor. So now let's delve into the first one, energy stored in a capacitor. So now the symbol, all right, we are having, energy is work in physics, all right, is W. So I have W here. Now, what is your quantity of charge in capacitor? Your quantity of charge is given to be CV, so you have Q is equal to CV. Okay, if quantity of charge is equal to CV, all right, this is supposed to be one particular charge. So that means when your capacitor is able to charge, all right, because now when you have a capacitor, let's say power bank as an example, all right, now before you charge, all right, you have zero because there's no charges at that point, all right. Let's say let's use a practical illustration of power bank and the phone. So you have a power bank and you want to plug the phone. So if the phone, all right, is at zero, okay, 0%, the phone is down, all right, so that means there's no charge, zero. So by the time you impute, all right, you connect your power bank with the phone, what's going to happen? There's going to be a change in the charge from 0 to another, a higher magnitude, all right, maybe to 5. So at the first point, your charge is equal to 0 when there's no charges. Then when there's now charges, you have a quantity of charge 1, all right. This for when there's no charge, and this for when there's charge. All right, so if that's the case, my Q is equal to CV. What's going to happen is that I'm going to be having my W is equal to, so I have Q plus Q over 2. The first Q, all right, is for when I'm not having a charge, which is supposed to be 0, all right. And if it's 0, I'm going to be having. Now, my W now at the end of the day is now going to give us 0 plus what? Q over 2. Okay, that's what's supposed to happen if you are following that. Now, let's look at something on this. So my Q is equal to CV. So I have what? 0 plus what? Plus CV. Okay, then this over 2. Then I have W is equal to, that is 1 over 2 CV. Okay, now that's what's supposed to happen. But if you are doing it in terms of your Q, you have Q is equal to CV. That is CV squared. So you have W is equal to, the first charge is another W, so we can write as Q, then plus another Q, then over 2. Then W is equal to, so your Q is charged, which is CV, all right. That is when there's no charge, and when there's charge. I've used that as an illustration before. So now let's look at the energy, all right, for the individual. Now, energy in an electrical system is given to be W, and W in electricity is given to be quantity of charge multiplied by potential, all right. Charge times potential, this is what the value of the energy. So if that is the case, if I'm writing for the energy of it, this in terms of the charge, but in terms of the energy, I have what? Energy stored 1, this energy when there's no charge, and energy stored 2, then everything over what? Over 2. I'll find the average. Then I have energy stored in the capacitor is equal to, what's my W1? W1 is when there's no charge. Like I use charge as an illustration, then that means W1 is going to be 0 if there's no charge yet. So I have 0 plus W2, then divided by 2. Then I have W is equal to 0 plus, what is my W2? W2 is also equal to what? QV. So I'm going to write QV divided by 2. Then I have energy stored is equal to 0 plus QV will give me QV over 2. Then I have W is equal to, what is Q? My Q is equal to CV according to the law of capacitance of the capacitor. So anywhere I see Q, I'm going to write CV, then into another V, everything over 2. So at the end, I have energy stored in the capacitor is equal to CV squared divided by 2, which is energy stored is equal to 1 over 2 CV squared. All right. This is the first value we can use to calculate for what energy stored in a capacitor. So if my W is equal to 1 over 2 CV squared, all right, I can move on ahead and write W is equal to 1 over 2 CV squared. Now, what is supposed to be the value of V if I make it in terms? So my Q is equal to CV All right, so let me find the value of V here. So what's going to be V? That is Q is equal to CV divided by C divided by C. So I have Q over C is equal to DC over CV. Then this one has gone. That is Q over C is equal to V, or V is equal to Q over C. So anywhere I see V, I'm going to be writing Q over C. That is voltage or is equal to charge over the capacitance. So I have W is equal to 1 over 2. My C, I'm going to write it. Then what is my V? The value of V is now Q over C. Then because of the square in B, I'm going to put square in that place. So what do I have at the end of the day? I have W is equal to 1 over 2. I have C here. Then I'm going to be having Q squared over C squared. Okay. Then W is equal to 1 over 2. C cancel 1 C here. That is Q squared over what? Over C. This equation 2. So we can use those two equations to calculate for energy stored in the capacitor. Alright. The first one is given to be W is equal to what? 1 over 2 CV squared accruing in that place. And the third one, right? The second is this first one. The second is W is equal to 1 over 2, then Q squared over what? Over C for energy stored in the capacitor. CV squared and 1 over 2 Q squared over C. Alright, so you can use that to calculate for energy stored in a capacitor anytime you are asked to do. Okay, so now let's move on right there. So, excuse me. So now if you are to determine, alright, so let's take two questions at least before we move on. Okay, there's a question here. The question says that a 300 nanofarad capacitor, so capacitor is 300 nanofarad, alright, NF. Okay, says is connected to a 250 volt battery. So my voltage is equal to 250 volts. Okay, then calculate the charge on the capacitor's plate. So you are looking for what? For Q. What's going to happen? You apply what? Q is equal to what? CV. So you can write that question down. Then I have Q is equal to, what's my C? My C is now going to give me 300 multiplied by 10 raised to the power minus 9. Then because this nanofarad means times 10 raised to the power minus 9, micro mu means times 10 raised to the power minus 6. So you are going to multiply that, then multiply by 250. So whatever answer you have will give you the charge. And the SI unit of charge is in coulomb. So you have at the end of the day, Q is equal to, if you multiply 7.5 times 10 raised to power minus 5 coulomb. Alright, that's what we're going to have at the end of the day. Okay, then you can also have check questions on series and parallel connection and solve them. Okay, now let's look at the next one, the charging of a capacitor. When you want to charge a capacitor, how do you go about it? And when you want to discharge a capacitor, how do you go about it? So that's the next thing we want to look at. So charging and discharging of a capacitor. So it's very easy. If you want to charge a capacitor, charging and discharging of a capacitor. If you want to charge a capacitor, all right, there's something we're going to do. There's a value you're going to have. And if you want to discharge a capacitor, there's also a value you are going to be having. Okay, so let's look at something right there. So for the charging of a capacitor, what you are going to do is that you are going to connect your capacitor to a source supplied, all right, a source that supplies voltage. All right, that's what you are going to do if you want to charge your capacitor. Connect your capacitor to a source that supplies what? Voltage. So you have a diagram like this. You have your resistance, your capacitor here. Then you have this diagram. Connect a source of voltage on it. So you have this diagram. Okay, then the quantity of charge needed to do that, all right, is given as Q is equal to Q naught, okay, open bracket, 1 minus inverse of lane, all right, minus T over CR. Okay, T is the time taken, this is the quantity of charge needed to what? Charge capacitor. I said first of all that if you want to charge it, you connect your what? Capacitor to a source, all right, then your total charge is given to be Q is equal to Q naught, 1 minus inverse of lane, raised to power minus T, this raised to power minus T over CR. CR here is what we call the time constant. What is time constant? Time constant is the product of capacitor or capacitance and resistance. Okay, the product of what? The capacitance and resistance is called the time factor. That's the current in charging of a capacitor. That's the charge in charging of a capacitor. Then the current in the charging of a capacitor is given as I, note these things, is equal to I naught, all right, E, that is inverse of lane, all right, raised to power minus T over CR. This is charging the capacitor, while this one is what? Current in the charging of what? Of a capacitor. Alright, so that is that we have on the board. So you can use those two things if you are charging a capacitor. Then in discharging of a capacitor, alright, what we do, once if you are charging, we are connecting it to a source supply. you are going to do the reverse case if you are discharging a capacitor. So in discharging of a capacitor, all right, you are removing it from what? From the source. So to discharge a capacitor, the post of the source voltage is reserved, all right, and the capacitor is set to what? Fully charged, all right. So when a capacitor is set to be fully charged, there is a value of voltage you are going to be having, and that value of voltage is going to be V, all right, of the capacitor is equal to Q naught, then E raised to power minus T over CR. This is what you have as the voltage of the capacitor when the capacitor is what? Is fully charged. This is quantity of charge when you are charging the capacitor. This is the current when you are charging the capacitor, and this is what you have as voltage when your capacitor is fully charged. V, all right, in capacitor is equal to Q naught, that is the charge, inverse of lane raised to power minus T, time taken over CR. I said CR is the product of the capacitance and resistance called the time constant. So you can use that. Okay, so if you want to discharge, if you want to charge, all right, you connect your what? Capacitor to what? To a source supply, all right. This is the symbol of the body. This is the capacitor, this is a resistance, and this is the source of that supply. So if you want to discharge it, you reserve it, all right. To discharge it, remove the post of the or reserve the post of the source voltage, all right. So and that's what we have when the capacitor is set to be fully charged. Okay, then once that is gotten, let's look at the other value. All right. Meanwhile, I forgot to tell you that aside from 1 over 2 CV squared, if you want to have 3 equations in your energy store in the capacitor, all right, let me just write somewhere so that you remember. You can also use 1 over 2 QV, all right, because Q is CV, so you now have CV squared. So 1 over 2 QV, 1 over 2 CV squared, and 1 over 2 Q squared over C. So that is what we have. Then right there, let us move to how to this last part we are considering. Okay, how to find the half-life. The half-life of what? Of a discharging and charging. Half-life. You know, in physics, in radioactivity, we find half-life. We also find half-life in what? In capacitor. So how do we calculate half-life? First of all, what is the definition of half-life? Right? What is the definition of half-life? Don't forget that I said time constant CR is defined as the product of what? Of the capacitance and the resistance. So what is half-life? You can write it down. Half-life of a charging or discharging of a capacitor. We have half-life of charging and we have half-life of discharging. So half-life of charging or discharging of a capacitor is actually defined as the time required for the charge in the capacitor to attain exactly half of the initial charge. All right. The time taken for the charge to attain exactly half of the initial charge is what we call the half-life of charging and discharging of a capacitor. So now in half-life we have total charge is equal to 1 over 2 of the what? Of the Q naught, because it is defined as the what? As the okay, out of charge of capacitor is defined as the time required for the charge in the capacitor to attain exactly half of the initial charge, all right, which is Q is equal to 1 over 2 Q naught. Now, if that is the case, how are we going to determine the half-life? If you want to determine the half-life of a capacitor, there are 2 formulas I'm going to outline on the board that you can use to determine half-life in case you have that in your exam. So the first half-life is going to be T half, all right, that is the symbol of half-life, T 1 over 2, okay, we have T 1 over 2, T 1 over 2 half-life, T 1 over 2 over CR over the time constant is equal to ln 2. All right, this is the first value of half-life. So we have T1 over 2 over CR is equal to ln 2. So I'm going to be having T1 over 2 over CR because I'm looking for T1 over 2, which is the half-life. T1 over 2 is equal to half-life. All right, so it's equal to ln 2 then over 1. So I'll cross multiply. So I have T1 over 2 is equal to CR ln 2. Or T1 over 2 is equal to ln 2 CR. So at the end, my ln 2 multiplied by CR will give me the half-life. So what is ln 2? Ln 2 is equal to 0.693.